Yep.
Awesome.
There's one more recording for you in a
Am I in
minute.
your way?
Yeah, I think you will be. If you can sit right here, though.
You can sit over there.
What if you sit in the middle?
Yeah, you get to take a fine spot if you want, because it's very nice to have the side to it.
I'll just,
Let me see what else I can do.
I'll just sit over here.
Thinking there's probably a chair right in the middle.
Oh, I'm trying to find a base for it, so.
Oh, okay. I thought you had a something for it.
Yeah, can you hold this while I dig? I may actually have it in my pack.
All right. You got it? Could you sit here?
We may use that chair.
Or sit where others are sitting so that you have a screen.
It just blinked out.
No, that's okay.
Okay.
Or whatever. Okay, that's cool. All right.
Or if you want me to film.
2 is better than 1.
Well, I mean, with that camera, I'm willing to hold
Yeah,
it.
go ahead. Yeah, that's fine. We can hold. Is that?
All right. So this is going to be rehearsed also, so it's going to be kind of me. It's my first time like doing the kind of presentation here. So the plan, as you can see on the right, is very simple. We're going to talk a little bit about analog electronics. So enough to get you going, like putting a fan or simple LEDs or something like that. I'm going to explain to you the rules in there, like basic rules of electricity. And then I'll dive into digital electronics like Arduinos, addressable LEDs, and that kind of stuff. And then I'll talk about the issues with wearables like wear and tear and all that stuff that can happen and how you can mitigate those problems. So the main principle is to keep everything simple. If you don't know how to do something and you go for like a huge project, you're going to fail. So you start simple. If you don't know how to do electronics and you can buy it off the shelf, just do it. You can buy like a simple LED like this and shove it somewhere, and it's going to look nice. Okay. So there's no point in like learning all that stuff. You're going to do something simple. Keep it simple. Okay. So you can use ELWAR, you can use the bullet I showed you, you can use garden lights. I think I have some garden lights there, like $5 at Walmart, something like that. It looks super nice. I have some of my costumes and they look really nice. They have all their flaws and properties, but like it's really cheap and you place it so you can replace it. You can toss the garbage and put a new one in there. So it's all good. I was going to put a picture there, I guess. Well, the main point is it's all about you expressing yourself and using electronics as a means to show something cool, not to show electronics, right? So for the analog part, I'm going to talk just about DC electronics. So I'm going to talk about voltage and current and power and how you can like do a very simple circuit and actually not make it blow up. So electricity is all about transmitting power to something so that it can use the power. Okay? So power is either dissipated through heat or to do something useful. And the more heat you dissipate, the more you drain your batteries, and the less time you have. So planning correctly your circuit allows you to not waste your batteries to do something useless for you. So for example, here I drew something with a diode. There is the resistor and a diode on the right. And the point is the resistor is there to make the diode work, but the resistor besides that serves no purpose for you because it does not display anything. It's just sitting there and sucking up your power. Okay? So power for electricity is volts times amps. Okay? And that's all very sweet, and that's a constant. So what is given by your battery as power is consumed by the circuit, and there's going to be a portion that goes to something useless and some portion to something useful. So bear that in mind. So here, for example, in red I put the heat dissipation, and in ugly color, the light actually that goes through. So an LED probably dissipates 50 to 60% of its power versus like a regular bulb is going to be 90% plus. So I'm not going to explain that too much, but basically the general rule when they teach in class electricity is to compare current and voltage to a waterway where the current represents the flow of the water. So how much, it's basically the flow of electrons that are going through. And the voltage is the height of the water. So the more height you have, the more you will push the electrons through. Okay? And so the multiplication of both of them is the number of electrons basically that are being transferred per units of time. I guess, like I said. So electronics is all, for these things, it's usually math. And there's two rules to follow. You have the notion of serial circuits and parallel circuits. Hopefully. So this is a serial circuit. And here you have two elements that are in parallel. Okay? So the rule is that the voltage as here is equal to the voltage as here. So this voltage is equal to this one plus this one. Okay? That's, you sum the voltage. For the currents, you basically have at the node, like an intersection, this is where you sum the current. So in parallel, you sum the current. So the current that goes in here is the sum of the current of this one plus this one. So that's how you're going to do the math to resolve equations. The thing is, you don't necessarily have to resolve the equations there. Like that. Okay. The other thing is that electronics is usually not very precise. We just use like 10% precision. The rest we don't really care too much about. We don't have to like be super precise. So like I said, it's not rehearsed. I'm sorry. It might be too fast or too slow. Anybody has any questions to what I said before, or is it okay? It's fine? All right. So basically when you build a circuit, you're going to create a relationship between voltage and current. And the different components will have different behaviors with regards to voltage and current. So for example, a wire, if it's ideal, has no voltage, it just transmits current. So what goes in, current goes out, and there is no difference of potential. A switch acts like a wire or like nothing. So it either has current passing or the voltage is the max. Basically, you turn it on or off. Okay? The battery, its purpose is to give you power, so it's going to have usually a constant voltage, more or less, and it's going to deliver as much current as you ask until it blows up. Okay? So if you go past its specs, it's going to overheat, it's going to fail in some way or some other. Okay? And the most common known component is the resistor. Its goal is to resist the flow of current. So the relationship is linear. It's basically the voltage is equal to the current multiplied by a constant, which is the resistance. And the diode is something that we like a lot because we have LEDs, which emit light. We have other types of diodes that do other properties. But basically, the principle is that usually it doesn't conduct any current until the voltage reaches a limit at which point it's going to give out all the current you want. So it basically switches on. Okay? The thing is, same thing. If you put too much current through it, it's going to blow up. Okay? Actually, you can make it pop. So you're going to have to manage the power. And when you make a circuit, which I should have put back here, like this one, the resistor is here to protect the diode from having too much current. So the resistor is going to define how much current is going through, and the diode is just going to suck it out.
So
Yes.
does the resistor keep a consistent current?
Yes.
Okay.
Yeah. So basically, you're going to have the equation V equals Ri, but you know that the voltage at the diode is a constant, and so basically R is going to give you your current because the diode does not give you your current. Yeah. So this is to show you how overwhelming it can be. Basically, all the components have properties that can be usually described as a schematic, what do you call it, diagram?
Yeah.
Those things, like what do you call those in English?
Oh, chart, a chart or graph.
Thank you, yeah. And so it's going to be a correlation between voltage and current. So I put in a battery, for example, which is going to be constant until you start messing up with it too much. Same with the diode. At 3.6 volts for this diode I choose, it's going to start conducting current. And if you look at the spec, it says it really wants to work at 20 milliamps. So you're going to figure out your circuit so that you're around here. If you're lower, you're going to have less brightness. And if you go higher, at some point you're going to go up the LED. And the higher you go this way, the less, the faster it's going to burn out. So its lifetime is going to be reduced. And this is a resistor. So it can go from being just a wire to being an insulator. And in between is going to be the value of the resistance. So this is kind of showing you the different curves. And so this is a typical diagram you're going to see if you're going to look at the spec of a component. So if you look at it, you're going to have like half a dozen of those. Some of them you care about, some of them you don't. Like the correlation between voltage and current you care, but they're going to they'll have stuff about like behavior when the temperature changes or some other properties, and you can bypass that because that's not something you're not going to be working at America or anything crazy. So here I just put like a way to solve the equation for a diode. And so I kind of touched on that already, where I know that it's a series circuit, so the current is the same everywhere. So the current coming out of the battery is the same as the one going through the resistor, same as the one going through the LED. Okay? It's in series, so the voltage is sum up. So the voltage coming out of the battery here is the sum of this voltage plus this voltage. Okay? And then you know the properties of the LEDs and of the resistor, so you can put in their equations. You're going to want the LED to turn on, so you're going to put the voltage at which it turns on, and you can resolve the resistance. And so you know what value you put in there. And when you plug everything in, it should work. Okay? And so this is the equation. So it's a little bit of math. It's pretty simple math for some people who have done some math. It can get a bit more complicated. The thing is, you can make something contrived or something simple. Like for example, this is like a throwaway LED thing where you just plug into a battery. The battery here is 3 volts and the LED is over 3 volts. So when you plug it in, it's going to work because the LED is not overpowered. And it might not be at full brightness, but it will work for hours. Okay? Sorry? Oh, okay. Feel free to interrupt me and tell me if you have questions or comments or anything. So there's a crap load of different types of components, and I'm not touching on all of them, but basically when you want to do something, there will be something that has been sold that you can find, that you can use. All you have to do is look at the specifications, how it's supposed to work. You can look at online resources. I forgot to mention, for example, for the LEDs, you don't even have to do the math. If you type LED calculator on Google, there's going to be like dozens of them that pop up. It say like what spec of LED, what battery you want to put in, and it's going to tell you use a resistor of that value, and it's going to give you the solution without any work at all. Okay. So you can use motors that are pretty common for Fursuits and other projects for like electronics, lights, relays and stuff like that are kind of used for more powerful things where you want to save energy to turn on some parts of your circuits. You can use solar panels and all kinds of stuff. So I was talking about the batteries. Batteries are rated for an amount of power. They're usually rated in milliamp hours. Okay. So when you do your circuit, you can measure how much power each part consumes because it's going to be in the specs again. So you know your current, and you know your the voltages of each part, and usually the power is voltage times amps. So you can compute how much you're consuming, and that's going to tell you how long your battery is going to last. Okay. The other way is to do an empirical. You just plug it in and see how long it lasts, and all of it. But basically, that's the principle. Oh, Yeah, and so yeah, different types of batteries, depending on size and so on, at different voltages and milliamp hours. So this is talking about efficiency. I'm not going to go through the calculation, but basically what I did is I computed the power being dissipated here by the resistor and the diode. And I see that in total I spend 180 watt per hour. And of that, only 42 is used by the LED. Most of the energy is spent by the resistor just heating up your fursuit. So there's other alternatives. One of them is a buck converter, which is a small circuit. I mean, if you want to talk about how it works, we can talk about it later. But basically, it's way more efficient. It's usually efficiency is between 70 and 90% for those, depending on where you are in their spec. And so I think I took 90% as an example of efficiency for this guy. And we see that it's only spending 5 milliamp. And so this is a circuit that spends 50 milliamp hours instead of 108, so it's going to last twice as long. So it can make a difference. So when I was building the slide set, we were talking about making a list of like useful circuits that you don't have to invent yourself that are pretty well known. So I put them there, like for example, how to amplify current, or how to hook up a relay if you want to ever put a relay in your circuit. How to use a transistor as a switch to turn on and off something. And then how to pick up a microphone or use a photoresistor, that kind of stuff. So this is going to be in the slides in case somebody needs it. So I think going pretty fast. So overall, we went over like basic DC, like during current electricity. I kind of talked about power, the fact that power is the thing that you are manipulating, and that the power is expressed in terms of current that goes through your device, and voltage, that's difference of potential energy, basically. Let's see what else. Also, don't make the math complicated. Just keep everything at 10%. Can somebody turn on the lights? Yeah. I don't know what's going on. Huh? Okay, well, that's fine then.
I think the switch is over there.
Yeah. This is kind of unrelated, but I wanted to talk about ELWAR because, like a lot of people like to use that. So there's benefits and inconvenience of ELWAR. It's very simple to use. It's off the shelf. The problem is I find it very fragile for wearables because when you twist it a lot, it's going to fail and break. So here's an example of 3 ELWAR that I have here. One that's working, one that's failed in some way, and one other one that's basically off because it broke at the connector. And the way ELWAR is built is you have a core with a wire inside and 2 wires coming out, and you just put current in the 2. And when it fails, the connection next to the battery, it's basically these connections here that broke. And you can fix them up. It's a little bit detail work, but like this is a picture of one of my ELWARs showing this. And so all you have to do is solder those 2 guys to the different 9 or power source.
You might have to speak up to drown out the...
Yeah, can everybody hear me, or do I have to speak louder?
Could I ask them to turn it down?
We could, but should I? It's going to be hard to ask them.
We'll just bang on the door.
Can you guys... we'll just ask. Can you guys in the back hear him?
You can?
Okay.
It's all good? Okay. So there's a bunch of tools that you need to make electronics. The main one is going to be your soldering iron. I like to have flux along with my solder. So basically you melt the solder on your circuit. And the flux is going to help everything become very smooth. I should have taken some of your photos there. The other thing that you're going to be needing is like a multimeter to see if there's current going through your stuff. Pliers, something to cut the wires. This is the tool. And then you're going to want want shrink wrap, which you put on your wires, and when you want to seal everything, you heat it up. So I put a lighter there, which should be the heat gun.
Real quick, it's heat shrink.
Heat shrink.
Shrink wrap is different.
Oh yeah, heat shrink. Yeah, heat shrink tubing. Yeah. I use these things are called helping hands because usually you're going to have holding your soldering iron. You want to hold your solder, and then you still have to hold your piece together to something else. So it's nice to have something that's using your third or fourth hand to put things together. This is a prototype board. If you want to experiment before you solder everything together, make sure it works. I have one here. Actually, it's the same one. Let's see. I'll go through my list. So, do you want wires? Do you want connectors? These are connectors, for example, or like clips or whatever for your project. So I should replace that. It's string tubing. Since we're going to embed stuff, we want some way to like stick everything together. So some form of epoxy or hot glue or something like that. And then in tools, you have soldering iron, multimeter, the wire stripper. I use this to cut the wires. The helping hands. I have a magnetic part bin for like my small screws and stuff that I can lose. Prototype board and jumper wires, a knife, screwdrivers, that kind of stuff. Okay. So this is going to cost you like, I don't know, $30. You can go to Harbor Freight and get a lot of that stuff for like a couple of dollars. Here's stuff that I pulled from our forum, from our chat room. Somebody was making a Freddy's Fursuits, so like keeping it a simple way. That was a bullet that she was using. Another guy is making a gun that's a fan for fursuiters, so it's like you wire all the fans together, wire everything together. So that's another thing that you can do with these electronics. That's been using it on another shooter. So you can make LED eyes also like that, just put an LED, it's very simple. And this is the cooling vest that was just putting batteries in there. Let's see if I can find some stuff there. Did I bring the power?
I have parts too. What do you want?
I don't know. I can't see what I'm doing.
Could you get? Are
I
those
was
the
going
light
to show
switches?
the EL wire failures.
Folks, I just want to let you know we're working on the lights. They should be back up in just a second.
That's cool.
Thank you. You could hold it up in front of the.
Yeah, no, yeah. So this is how they fail. Right? So you have a working one. This one starts feeling like cheap China crap.
Oh.
Okay. They're all cheap China crap. Okay, because I'm cheap. And this one failed probably here at the connection, and so there's no more power going through it. Yeah.
Oh, there goes the other
Yeah,
one.
yeah, it's, yeah, I quite shorted everything.
No, you're good.
It's because there's a short in the purple one. So that's kind of why I stopped using yellow wire. Well, you can use it, but as long as you're okay that it fails and you can replace it, it's, you know, it's got everything. Yeah, electronics is a great friend in person because you're going to have to pull stuff out.
Really tricky.
Yeah, I mean, this one's also,
So-
I can get it to turn on.
Yeah, yeah. It's,
by squeezing and moving it, I can get it to turn on.
That's really cool. Yeah, right.
can you see it?
This is literally Michael's.
Yes.
Here's garden wire.
Hi. Yeah. Yeah. That's good example right there.
Yeah, that's great.
It's a bit too dark. Yeah.
Garden wire.
It's garden wire.
Can you come over to get more light to show it?
Sure.
Yeah. Here, can you show it to the camera?
Garden wire from Michael's, of all places.
Michael's is where pretty much all of this came from too. So.
Really
Yeah.
cool.
Right on. Very
go there all the
cool.
time.
I like it.
I made a little pouch for the battery pack.
Oh, right on. Yeah, that's another thing.
Yeah.
That
Learn to
is-
distribute the weight.
Right.
But earlier today it unraveled because it just wrapped around.
Oh, okay, right.
You could probably just do like a stitch or two to
Yeah, I
keep
think
it.
I might do that.
Oh, it's really cool.
Thanks for sharing.
Yeah.
So here's some examples of stuff you can buy ready-made. So a bullet, a small thing that you can pin to yourself, and I think this was for a frisbee or something, and kind of hack it together. Actually, pass it around or
I
something.
will, sure.
Right. If I find all my stuff, I might be able to turn on something later on.
Okay.
All right. We're going to talk now about digital electronics. Sorry. So things are a bit simpler in the digital world when it comes to figuring out voltage and current. You don't have to deal with that usually. Usually everything is 5 volts or 3.3 volts. So that's the only thing you have to pay attention to for the logic signals. What you're going to be focusing on instead is devices and things that you control. So they will sell you parts that are assembled that have a property. For example, a gyroscope or an LED or something, and you just want to tell it what to do. And that's part of digital electronics where you do the programming. So if you look at the signals on the wires, it's going to be 0 volts usually, or 5 volts for logic false or logic true. But it's going to be tolerant. So if it's like 1 and something volts, it's usually going to be seen by the device as false or 0. And if it's over like 3.5 volts, it's going to be seen as a 1 or logical true. Okay? You do have to pay attention a bit on the voltages. You will currently see 3.3 volts, 5 volts, 9 volts, 12 volts. So you have to choose which standard basically you're going to be working with. And it's going to be depending on your project. If you make a big project, you want 12 volts because you want to flow less current and more voltage. If you do something really small, you're going to use less voltage and more current because it's going to be more efficient. Most of the boards that you're going to be using are going to be 5 volts or 3.3 volts. If you need to juggle between 5 and 3, you can use buck converters or some tricks. There's usually ways to go around because people have that problem. So it's usually not a very difficult thing. You just have to be aware of it. And when you combine things, the ground or the negative side is usually common. And like for example, if you put multiple batteries, you're going to connect the ground together and you're going to feed the positive side to the different parts.
Why would you connect the ground together?
Because it's going to be your reference point for the voltages. That's going to be your 0. Okay. Otherwise, they're going to be floating, and you could have like the two sides don't know what they're talking about. The reference is not there, so they might see something that's like a number they're going to make up based on the humidity in the air and things like that. So this is an example of a parts bin that I have where I have a bunch of random stuff that I've played or not played with yet, like LCD screens, keypads. This is a motion sensor that detects how far you are, like you basically see Kinects and things like that. That's the kind of stuff you can use. There's an LED here. That's the LED, which I don't know why I have that. A lot of resistors. I try to not use them. A lot of wires. These are variable resistors. So there's a bunch of stuff that's available, and all of it is like usually $1. It's not much. Sometimes it's like 10 for $1. But you have some cool stuff, like the really cool stuff maybe is going to be $5-10, like a gyroscope that tells you like the position in space. Let's say you want to do a fursuit when I'm going to move my tail and it's going to change colors as I move. You know, you put something that's going to sense the position, which is going to talk to your board, and you're going to use the library, and it's just going to go like, hey, when it's there, I want that color. When it's there, it's that color. So then it does that all by itself. It's not necessarily very complicated. Usually those components are going to talk to each other through a protocol, like the standard peripheral interface, I believe.
Yes.
SPI.
Standard peripheral interface.
Yeah. Serial protocol. One more is the LED protocol I use because it's the smallest, least number of wires.
Oh yeah.
So you probably have heard about the boards. So you have the Arduino family, which is what I use, and you have, for example, the Raspberry Pis. And like at first, when I started all this, I did not know what the difference was between those and why you would have so many different choices. The truth is, the top one is a controller, and the bottom one is a mini computer. The Raspberry Pi is going to have an operating system, usually Linux. It's going to have a lot of cores. It's going to be gigahertz, and it's going to be consuming probably 1 to 10 watts, which doesn't seem like much, but when you put that on a battery like this, well, it's not that much time, right? And also it's going to be a bit bulkier. It's going to be a bit bigger than this, and so it's not really for like simple stuff like this. It's going to be for like really big projects where you're going to create a bunch of stuff, and it's going to be harder to program actually. The Arduino, on the other hand, is going to be boards like this to something really small, like my controller. This is I think that's one of my original controllers for my head. The chip is in there, okay? And the bulk of all this is the wiring, okay? So why do we use Arduino and not like some manufacturers like specific board or anything like that? It's because it's a whole ecosystem. Everything has been made for the hobbyist. And so when you jump in there, you're going to have a whole community that's going to be there helping you to move forward. You'll have libraries that are shared by everybody that are going to be free usually. You'll have a website with a forum where you can ask questions, like you can ask like, what is C language? And so somebody might respond to you like, go look at that website, or like, how do I program that specific protocol? So you have help. There usually is, so there is going to be a controller on there, which is this big chip there, plus a bunch of crap around it is going to be like something to give it a clock, something that's going to control the USB port, and that kind of stuff. It's all integrated, it's all standard, so you don't have to worry about any of this. Okay? And also, parts. If you want to have a project like you want to do home surveillance and you want to like not have to figure out how to wire a bunch of cameras and whatnot, you can look online. There might be a board that you can just plug in there where you have connectors for the cameras and the libraries and the software, and all you have to do is just Lego everything together. It's going to work. So this is one of my boards that I use to actually program other things. Usually what I do is I connect things. So the board is below and it's got wires connected to the thing I care about. And this is the thing I care about, so I have the wires going there. it looks messy because wires are bulky, but otherwise it's pretty simple. And the board, a controller will have pins that do input and output. And so each pin is going to be in the software accessible directly as a port, and the ports are going to be grouped in 8 bits because the controller works in bytes. So each bit is going to be controlling one of those pins, and the port is basically going to be with a letter and a number. So it's going to be from A0 to A7 is going to be the first register that's going to handle port A, and then each pin is going to be 0 through 7, or B 0 through 7, and so on. So if you read a little bit of the documentation, you will know exactly where it comes out here, and so you can read the value in there. So if you put if you put your battery in there to 5, for example, it's going to read that you have a 1 there. If you remove it, it's going to see this is 0. Okay, put it to the ground. It also has other. Sorry? No, okay. You also have other ways to access those pins. You have analog input and output. So if you put on the pin something that's not a 0 or 1, like 0 or 5 volts, like if it's 3.7 volts and you really want to know it's 3.7 volts, you can use it as an analog I/O. So it's going to use a whole register, and it's going to convert the voltage that's there into a value in that register from 0 to 255. Okay. And there's also ways to access the ports as protocols, like SDI, serial ports, and so on. Usually the ports have control and data registers. The control register is going to decide whether you want to read and write, whether you want it to be analog, and so on. So that allows you to configure your device the way you want to use it. Alright, so Arduino comes with an IDE, which you download from the web and install on your computer. It works with all platforms, Mac, PC, and so on. This is what it's going to look like. It's very, very obvious. There is a pane when you're going to be writing your program, and you're going to have a status pane that's going to tell you what the board is doing. The environment is going to give you the ability to program in C++ your device. It's going to allow you to compile and upload the code into your device so it runs there. And if it doesn't work right, you can use the interface to actually debug. There's also a ton of libraries, as I said, that allow you to do all kinds of stuff that you match to the devices that you purchased and you want to plug to that thing. So Arduino is, because it's kind of a public domain,
Open source.
Open source, thank you, design. There's a lot of people and companies that have developed their own boards, and so the IDE allows you to upload the definition for your board through the board manager. So in your menus, you can go to the tools, and you're going to go to the board manager and follow the instructions to install the definition for your board. After that, you just select it, and it's ready to send it to your board. Just read the documentation for it. Okay. You may have to specify the USB port. So you're going to have a bunch of USB ports on your laptop, and usually it's going to, when you plug your board in, it's going to detect, hey, I'm on port 5, USB 5. And so the port's going to say, hey, you have 3 and 5, and on 5 you have your Arduino. So you select that one, and you can download it. Yeah. So basically, how it works, you install your IDE, you load a program into it, you can load a demo program, you take your board, connect that with the USB on your laptop, it's going to detect it, and you can upload to the board the program, and it's going to work there. Of course, you need to put stuff in there to you see that it's actually doing something. So there is a test LED light that you can use for your first example that's built in. So you can see it's blinking or something, so you know that you actually went through all those steps and you got it right. And then after that, you go to the decoy and you just plug that crap on top and have that light up until you make your fursuit. So one of the main challenges of Arduino is to actually code all that stuff, and so you have to kind of learn C language. So at first you don't have to, you can just look at the libraries that will come with demo code. You can just steal that and upload it and see if it works, and maybe it's good enough because you're okay with the rainbow pattern or something, so it's just going to be nice and shiny. But in the end run, you're going to get bored with that, and you'll want to do more stuff. So you'll have to learn about, how to do things repeatedly, how to store information so that you can, display one thing and then another, and then you want to put a switch in there so you can change mode and that kind of stuff. So you have to store information. Okay. So again, there's a bunch of stuff online that you can look for that. So, programmable LEDs. There's all kinds of types. The main ones you've probably heard about is the dot star or NeoPixel, WS2012, if you want to use. These are buzzwords. If you look a little bit, you'll stumble on those. And these are those guys. And that's what I'm using in here. So the benefit of these is they are programmable. They have a chip inside that handles everything. All you have to send it is colors. So the protocol is you send it like 3 or 4 colors and it's going to display it. And the other thing is they're connected one after the other. So you're going to send the colors down and they're going to trickle down and light each one. So in terms of wiring, it means that you only have one wire to solder. So if I want to connect 2, I connect the data here and the power, ground, and 5 volts to the next one up, and it's going to keep going. So it makes it very, very simple to develop nice looking stuff like this.
And they're addressable, right?
Sorry?
Are they addressable? Like
These are
each
addressable
LED?
LEDs, yes, yeah.
So it doesn't just copy the same color all the way down?
No. It's each LED will have the color that you decide to put on it. Yeah, one of the problems with these is they break also. And so I think I had brought, actually my fursuit broke. So I can show you later, but it's supposed to light up the front and the back. And the back broke halfway, and so I will have to go in there and fix it, because my build is actually pretty janky. It's not meant to be super robust. It was my first one. So for the LEDs, you will not only figure out how to talk to the LEDs, so you're going to be using libraries. I put some references here to the main libraries, Adafruit and Fast LEDs that you can pick up. The third one is mine, so that's my plug. I've been trying to develop my own version that has different properties that I prefer to what they made. Oh yeah, installing a library in Arduino is you basically copy the thing you downloaded into the library directory, and then you restart the IDE and you should see it as a...
The newer IDEs, there's actually a menu that lets you manage libraries.
It's about time.
and you can actually search for these by name, so you don't actually have to move anything in any folders. It'll do it for you.
If I have to register, I should do that then.
Yeah, it's a really cool feature, because it'll even update when you get new versions of the software.
It's good to know. I didn't even know about that. So thanks. Yeah. So it's even simpler. What the heck? Yeah, my slides are over there. So last part of the talk is going to be about actually building wearables and the problems you're going to encounter. And it's all going to be that you want to build something that you can do maintenance on, and that's going to be resilient to the abuse that you're going to put on it. So you have to think ahead of time what's going to happen to your thing. Like, how dumb am I going to be, or how dumb is the guy I sold it to is going to be? What can he fuck up that's going to happen? Because it's going to happen. Okay? Yeah. one of the things is some people like sweat a lot, so you have to take that into account. You're going to have to place your batteries away from the humidity, or you have to increase it to something that's waterproof. They don't really like humidity. None of the electronics like humidity. Okay. So for these LEDs, for example, there's different standards of weatherproofing from IP32 to IP67. So you get something better than that. This is IP67, so it's coated with a silicone sheet. So if you seal the ends, it's watertight. So you can like dunk it in your bathtub if you want. For your boards, you probably want to put them in a case of some form. Here, for example, my hardening here is to put the chip in here and like coat it with epoxy. Once I've done epoxy, then I put shrink wrap on it, like multiple layers. For hardening, because stuff like is going to be tugged a little bit, I don't expect like super high activity. I did put some shrink wrap extended so it doesn't like just like end where the wire is soldered, to have the shrink wrap take some of the flex and basically relieve the stress points. Okay, so that's one way to do it, and so far this has worked for me. This is failed here because it's disconnected, because this has like recessed a little bit because my thing is not long enough. It's kind of things you have to figure out.
Is that shrink wrap or heat shrink tubing?
Heat shrink tubing.
Okay.
Yeah. Forgive my English.
No, it's fine.
So I'm going to pass that around so you can see, like, this is not good enough here, and this I think is pretty okay.
All this time I've been seeing shrink wrap in the forums, and I thought it was just normal shrink wrap.
No, it's just
from the kitchen.
It's my Franglish.
No, it's fine. That's fine.
Yep. No electrical tape, ever.
Yeah. So electrical tape is disgusting. It's gooey. It's going to slide. It's basically a band-aid to your electronics. So avoid that at all costs.
I mean,
duct tape is better. Okay. Yeah.
well, you can use it as a quick repair at a con.
Yes.
Yeah, sure.
But as soon as
But you can use shrink wrap too in that case.
Well,
the
I mean,
actual, yeah.
If you don't have any shrink wrap
Yeah.
available, or if it's deep inside, you can still use electrical tape. But if you're building it, don't.
You shouldn't even own electrical tape. That's my point. It's a waste of your money.
Oh God, I have some in my pocket. What's wrong with me?
You're a failure.
Well, no, that's for repairs.
Actually, I use it for my antlers.
You have it ironically.
Exactly. Circle and a line through it.
So if you're very, what do you call that, scared that you're going to have to deal with a lot of humidity and so on, you're going to use waterproof connectors. I think that's what Emblade uses on these suits. He sweats a lot, so, and his electronics are all over the place. Otherwise, you should...
Emblade.
Sorry?
He was asking who? Emblade.
Hold on, let me show you a photo of Emblade. Do I have a photo of him? That's Emblade on the right. On the right. Yeah. So he's got LEDs all over his body. Here. So he's gonna be sweating a lot. As my stuff is more on the muzzle, so it's away from my sweat, and so I don't have as much of a problem with that. Okay, great. Go away. Great, that's not awesome. I lost my slides. That's my slides. Oh, shit. Sorry about that. All right, back on. for the batteries, you're going to, sorry, back online. So for the batteries, personally, I try to not have prongs sticking out because I don't like to be electrocuted and I don't like to have them short. So I prefer to put like the female connector side on the battery, or use things that are protected. Like this is a power connector. These are just clip-ons that you use for underneath and stuff. That's my preference, but I don't always abide by that rule. What else is there about moving on?
Maximize or presentation mode.
So this is preview for PDF, so,
I can't see anything.
The window itself, maximize the PDF viewer, maybe.
So about the wires, so you have an example of the wire that I built with like something that's a bit failed and something that I think is a bit alright. You have to take into account they're going to be tugged on, that they're going to be bent, that they're going to be like stepped on. I mean anything, you know. So when you build them, one of the things you can put them away so they're not like immediately accessible, so that like when you put your suit on, you're not going to like just grab the wire and just like yank on it as you put your arm in there, or that if you yank on it, there's going to be a relief point. Like for my fursuit head, for example, when I built it, I simply put a piece of Velcro that protects the wire. So this is the power, so I can pull there, it's not going to pull the rest. Okay, and it's basically blocked by the connector itself here. Right. So this is the relief here. Okay, and this is my new controller. I can show that later. So this is my relief. Okay. Right. So this is sewed on.
Yeah, that's smart.
Yeah. Well, that's that, or do the repair at the same time. Eventually, you understand.
Yeah.
need that for the, need your other hand.
Hmm?
You need your
Oh,
other hand.
thank you so much. I think, there we go. Thanks, appreciate it.
The other ways you can do stuff, if you do something that's more permanent, you can always sew the line in a zigzag. And so if something happens, you're going to break a few stitches, and you'll know that something has failed and you need to do the stitches again, but you have saved your electronics. So let's say you put something in a box, for example. If you're cheap, and it goes in your box, you can just like put it like this, and you yank, it's gonna pull everything that's inside. You could just do a knot, and if it yanks, it's gonna pull the knot and the box instead of what's inside. So that's usually what's done for like really cheap electronics, because it costs nothing to do. You can also use grommets, and if they're tight enough, they're going to hold up pretty good. Let's see. Oh yeah, if you're going to have connectors between parts, like let's say you're going to make like the whole suit, and you're going to have like the body and the head, and they're all connected together, and it's going to take you like 45 minutes to plug together. One of the things that's going to happen is sometimes like you're going to overheat, you want to take your head off like real quick. make sure that you plan for that. So either you have a really long wire that's going to spool out, or something that's just like pop and disconnect, and then you toss the head and you go back, oh, I'll just clip it back on. So if you have a locking connector like this, it's going to hold up pretty good. It's going to yank something else. So this is not what's going to fence, something else. It's going to be this part. It's going to be my connection here that's done with duct tape. So think in those terms of what is going to be the point of failure. Okay, that's important. I'm going to talk about these LEDs. So these are, I should have passed that along. So this is a LED strip. Yana was here for a while, but he has LEDs on his ears. The problem with these is, so this is our standard 2812. Okay. The problem with these LEDs is they're like nice and flexible like this, but each LED is soldered on at each spot, and so the more you do this, the more it's going to wear on the solder joint, and they are going to break eventually. The worst part is when you wobble them like this. It's going to put a lot of stress on that, and this is going to make it fail prematurely, and you're going to have your LEDs that start like acting really weird because the ground is not going to be there or something. So be aware of that. So when you use something that's flexible like this, it does not mean that you can just like put it everywhere and it's going to flex. It means that you can mold it to something that should hold it in place. Okay. So if you want to put that on something that's going to flex, it's highly recommended to put something behind. It's going to be like some sturdy plastic that prevents it from at least flexing this way. And so for Yamaha, for example, at VLFC, the year we built them, some drunk dude that was not part of the con was like, "Oh my God, a bunny is so cool!" And he grabbed his ears and like tried to pull him out of the elevator, and basically broke the electronics. And so this was the first project, so we made it like nice and tucked in and everything. And so to repair that, we had to basically undo everything and put something else. And so that was a problem. The other thing is, if you see him at the dance, his ears kind of wobble at the top a little bit. And that's the same thing. The wobble would do this to the LEDs over and over, like for like many parties, and eventually they fail there. So he fixed that by adding wires at the flex points and change where the flex is going to be. And he also added the backing. Okay, so these are things you have to take into consideration if you're going to play with those.
When you say wires, he's not just gluing them as reinforcement. He's like cutting the.
Yeah, he basically cut the thing and wired and used wires, as far as I remember. Yeah. Same thing here. Like if I flex this enough, this is going to fall off. Okay. So what's going to be flexing is those guys. You might want to look into silicone wire. They are really nice and flexible. I have some sample here. You'll see the difference between regular and silicone wire. So that might be a good place to use those. Let's see what else. I guess that's it. Oh, I brought some shrink tubing. I have different kinds that are available. So you have the regular ones. This is from Harbor Freight, so it's like $1 for a whole bag. It's not the best one, but it works fine. This is shrink tubing that has, I think, hot glue inside. When you shrink it, it melts and it becomes like nice and hard. The thing I pass around here has some of it here, and it's yeah. Pass it again. The transparent one around is this guy. Actually, both of them. So that's going to seal the connection for me. So that's pretty good. Some points of failures. So I put some photos of random points of failure. This is what's called a cold solder joint. Basically, the component has wobbled and broken the solder. So sometimes it contacts, sometimes it doesn't. You have those failures in your car, for example, and you're like having a repair or like changing some part of your car is going to be simply the component that failed like this because it's been vibrating for like 200,000 miles. And so you have to be aware that this could happen if you put on electronics on something that's going to be vibrating a lot. about power and duration. So that's one thing I was struggling with my fursuit. So you have two schools of thought. Bigger is better. This is not powerful enough because I cannot run my program. So I'll just put like the next bigger thing. I'll put like a 1 gigahertz CPU and like a gig of RAM instead of like using 16 megahertz and like a few hundred Ks. Same thing with the power. You can go like, this battery doesn't hold that much. It's what, like 5,000 milliamps. My 2,000 LEDs there, last only 20 minutes. So I'm just going to do like make a big tail. I'm going to put like a huge battery pack in there. So it's different schools of thought. I am from the embedded side. I want everything small and like super efficient. And so I spent a lot of time when I was coding this to figure out how bright I can have those LEDs and run. So I had to basically do some measurements to see that I was not drawing too much. So my brightest mode is actually overheating my battery bank, and the lowest modes are actually barely drawing on the device. So there's tricks for that. One is how bright your LED is running. Secondly is how many you light at the same time. So for example, I have a lot of dynamic modes where I'm going to be actually at full brightness, but they're like I have the black and white swipe. It's just swipes there. There's only a handful of LEDs are on at the same time, so that doesn't draw too much power. So because the eye has a sense of perception, doing a lot of motion allows you to have something that looks cool without sucking up all your power, right? Like here, for example, I have colors like shining and sometimes it's going to flash. It's going to attract your attention, but it's not going to use up all the battery, okay? If you have something that's going to be really bright for even a tiny fraction of the time and you're like at the limit of your battery, you might cause something called a brownout, and it's not going to be reliable. And so you're going to have like the thing reset or something weird going to happen. It probably means like you're stressing your battery, okay? So there's multiple ways to figure this out. So when I did this, I was eyeballing the power consumption by knowing the spec. Like, okay, this is going to draw like 60 milliamp at full power. So if I use half the brightness, it's going to be half the power, that kind of stuff. And so I did my rough math like this. Another way you can do this is to verify with something that's going to measure your consumption. Like these devices on the USB port, or this on the power plug if you're going to connect it to the power. This is not very precise, by the way. This is kind of precise, but it gives you this is all about doing ballpark solutions. So if this shows you it's okay, it's quite okay. And then you validate this by actually running it and see like, is my battery like heating up? Is it like lasting as long as I was expecting? If not, you kind of tweak it afterwards. Okay. Yeah, there's maybe at some point you'll read about this, but it's often that we put capacitors next to the components to prevent them from brownouts. Because when you draw something from the battery, it might have a voltage drop on your power line, and so this is going to like keep the voltage for a fraction of the period of time next to your component. So one big thing that we keep talking about in the chat room is safety with batteries. There's different types of batteries around, and somebody who uses a lot of power is going to have to use a battery that basically is more dangerous. And so Emblade, for example, uses, I think he uses lipos, right? Lipos are kind of...
I thought he used the life.
No, these are...
Oh, he goes?
No,
all right. I don't know.
I don't think he does.
Okay.
He
probably
RC.
advocates and tells everyone to use the life pose.
Yes, because they're safer.
Yes,
Yeah.
but then he uses lipos.
But he has a lot of RC stuff, right?
Right.
So the thing is, because he's afraid of this, he has that encased in a fireproof bag in his suit. The other thing is you want to put your battery away from your face, away from like parts that you want to keep intact in your body, okay? Right? I have an example with Zarapar, for example. Somebody, actually a friend of ours, made him a simple fan with a battery, 9-volt battery. But the guy did not really know yet how to do that right. And at some point it shorted. And when it shorted, the battery overheated, and it burned him in the face because he put the 9-volt battery close to where the fan is. It's in the head, and so bam, he got burned. He had to toss the head out and like get the battery out because it was like close to getting hurt, right? So you have to take that into consideration when you are going to be putting power in your suit. Emblade uses a lot of power because he's a tension bore, and so he also uses fuses to protect himself. So if something shorts, the fuse is going to blow and protect him from having the battery like dropping all the current and either shorting him or like catching on fire. Okay. I don't do that because I use power banks, like USB power banks. Please.
I've been toying with the idea of using a drill battery, a DeWalt.
A what?
A drill battery, DeWalt power pack. That's using, I believe, it's either lithium ion or
the new ones are lithium ion, I think.
Yeah, the LiFePO or it's one of those two.
LiFePO is pretty expensive, right? So.
But and then just dropping it down to like 12 volts.
If you open your DeWalt drill, you'll see that the battery is the same one you buy.
They're a whole bunch of 18650s.
Exactly. Yeah. Or 18 whatever if it's lithium ion. Yeah, slightly different.
Yeah.
Versions. Yeah. But my point is maybe you're better off buying like Samsung batteries straight up instead of like going to DeWalt.
Well, the reason why I was looking at doing one of those battery packs is because this is something that you can clip in and easily remove from your suit to charge and just swap out.
So 18650s, if you look on eBay, you will find holders the same as you have for AA batteries.
Yeah.
And so you could use that and just clip them in and out. I actually have that for my cooling vest. It's 3 18650s, and it's just like clip in and out. It's just a battery holder. Yeah.
Are you able to find waterproof ones?
No.
Okay. That's the other reason why I was looking at the DeWalt.
Okay. Yeah.
Because they are going to be much more water resistant. Because I don't want to get sweat into that.
Yeah. The other way is to put it away, like in your tail or something. It's going to be heavy too. So where do you want it? And it's going to be bulky. Do you want like a blob here? Do you want it like?
I was thinking about here.
Yeah. Well, that's kind of where the tail would be, right? So.
Yeah.
I mean, my point is going to be yours to decide what you're going to be doing in that space, you know. It's all about tinkering and hacking that stuff.
Oh, yeah.
The big trick with those two is if they're 12 or 24 volts, unless your system is using that, you're going to have to step down with the regulator, and that's going to add a lot of heat and a lot of waste of your energy.
Well, it was going to be a step down
like you
from
want
20 volts.
You want to like aim the battery to be as close to the actual, because then that's a lot less wasted energy in the whole system.
Well, if it's a 20 volt, the line is going to drop much less power anyways, so he doesn't have to draw a big wire. Yeah, the reason to have, yes, sorry.
Is sealed lead acid just too ridiculously heavy?
Yes.
Okay. You can try a car battery or a go-kart battery.
Well, I mean,
an alarm battery, but
if you want to do like a car furry, you could do that.
I've seen
it would make a lot of it would make a lot of sense to do that.
The main thing is you're going to have to look is the properties of battery, right? It's going to be a power to weight ratio. I don't know if actually lead acid is way heavier for that than other types. It's also going to be depending on the form factor that you can find them at, and also the properties like how fast can you discharge them, and how fast you need them to be discharged to do the effect you want, right? So you have to take that into account, and also the cost. Like, are you willing to spend like $200 for it, or you really want to like go buy this for $10, right? I'm cheap, so I do everything cheap. And if I lose it or I break it, I'm not crying. Right? Any other questions? Yeah?
You talked a little bit about the fireproof bag concept. Like, how would you make that? What would you feel is a trustworthy construction?
I personally don't know. You could join a chat room and talk to him later, and he will tell you, or maybe...
So I chatted with him about that, and he said, so let me turn around real quick.
It's usually something like fiberglass.
No, so the question was about the fireproof bags. There you go. Thank you for that. I'll let you film the rest. But yeah, the question was about fireproof bags, and Emblade is a big component of those and he buys those already made. Like they make bags that are transportable, and then he just seals up the wired entrance exit so that it's a sealed bag that's waterproof, fireproof. They're just for transporting in airplanes and boats and what have you. So it's mainly for transportation.
But it's okay to use in C2, like you could run battery power from it.
Yes, exactly. Yeah. So.
Disclaimer, I didn't say any of this, right?
Yeah.
Right. No, this guy said it was okay.
But this is probably one area where you don't want to build your own. You want to buy something that somebody's rated as fireproof.
I'm pretty daring, so that's why I was trying to gather whether I'll buy it. That makes sense.
So the trick is to not drain your battery too fast. You should stay within the specs so it doesn't stress, it doesn't like go into a mode where it's going to be dangerous. So you're going to have to do a little bit of research and invest some time talking to people, see what they've done, and come up with a solution that you like, that works for your specific project in terms of cost, performance, and all that. So you're going to have a balance of all those, right?
Well, I got one more thing on that, by the way.
Yeah, please.
Since we're talking about Arduino sensor, you can also get a temperature sensor and put that next to your battery pack and have it do an automatic shut off as a safety check.
Yes.
So if you're more programming, savvy, that could be a good way to keep everything safe.
Yeah.
Or just a thermal fuse.
Yeah, fuses are
yeah.
obviously a good idea.
Always have a fuse.
Yeah, I don't do that because again I'm
Never
I'm
refuse.
hacking everything.
Never refuse a fuse.
So
That's your problem.
maybe last few words. There's resources online for everything. The internet is your friend. If you want to buy stuff, so I will make the slides. They're the Google slides, so they'll be available. So places where you can find your stuff. So you can go to Fry's, like you have to buy your stuff like right now, and you can go next door, like a few miles away, and buy that on a brick and mortar store. If you're looking for some like cheap stuff, weird stuff, like used batteries or like a fan that you don't want to buy new because you want to buy something that's like powerful and that should be like $100, you might be able to find in like stores that sell secondhand stuff. So in the Bay Area, there's weird stuff and halted computers that are pretty well known. I bought like UPS batteries there for like $5 when they had them. I had to come with a voltmeter because I didn't know if they were selling garbage or not. And like a load to see that it was actually kind of working. But you can buy stuff for cheap there. Otherwise, there is a bunch of sites that are going to be sending you like dev kits or like cool stuff. So the sites usually that are in the US will sell you stuff that's reliable, that has been tested and curated. But if you don't have the finances for that, or if you want to be a bit more exploratory, you can go directly to eBay or AliExpress and get the original parts from like a manufacturer for like pennies on the dollar. You're going to have to wait like 6 weeks for it to arrive, and the service is going to be what it is. It might be like the colors are off, or it doesn't matter. Usually everything's fine; it's pretty much the same, but you have no guarantees. Okay. But usually AliExpress is going to be cheaper than eBay. Otherwise, places where you can learn. Electric has a lot of great tutorials. Phil has made a lot of those, and he's here, he's a furry, so you can ask him like cool questions about it. I'm sorry, I spilled the beans. Okay. Otherwise, the Arduino website is where you're going to be downloading the IDE. You have like man pages, tutorials, forum, all kinds of stuff for that. And also, if you have a chance, go to one of the maker fairs. It's a freaking exciting place. And if you're like, haven't done your project yet, kind of want to, you go there, you'll be coming out, you'll be so pumped, you'll buy the shit right there, and you're going to start making stuff, because...
And they might also let you make it right there.
Yeah. It's a maker fair. The maker fair is amazing. It's really a place to get energized for doing like really, really cool stuff. So that's also a place to go to.
Oh, yes.
There's probably other things like Mashables and so on. Yes?
As a Fry's employee, I will comment, be ready to cross-reference. The brand, the particular brand that is carried for most digital stuff uses wildly different part numbers from literally every other brand in the industry. So be ready to cross-reference if you're rushing there to replace something.
I rarely go to Fry's anymore.
Yeah.
Yeah.
Not as a Fry's employee, fair enough.
Yeah.
The NTE part number versus the industry
Yeah, the
part number.
NTE uses ridiculous part numbers.
Yeah.
So specifically go to nteinc.com if you're rushing there, because that'll save a lot of time.
Okay, please.
Okay, one other thing is that not only Fry's, if you don't have a local Fry's, there's also Micro Center,
Oh, yeah,
which
Micro
is
Center,
in
yeah.
the SoCal, also West Coast,
Yeah.
East Coast.
That's
A lot, it's like heavy in the East Coast. There's not even a Fry's over on the East Coast.
Yeah. We kind of lost
And-
those. We used to have those here. Yeah, please.
Related to battery packs and AliExpress and eBay,
Yeah.
be very careful buying like even USB battery packs. You can get ones that already have the dangerous wiring built in for you, so you can do everything else right and they'll still catch on fire. So spend more on the.
All right. Quick note about batteries. If you're going to be buying like 18650s or whatever, buy a brand. Like buy LG, buy Samsung. Don't buy what's that? Surefire. Yeah. I mean, seriously. Yeah.
Well, hey, how about a tire company called Mayron?
Those actually exist.
Yeah. No, so basically, if you go on eBay, 99% of the listings are going to be like Surefire or equivalent like knockoffs in China, and usually the ratings are like ridiculous. They're going to say like 10,000 milliamps or whatever,
And they don't.
and you take it and it's like 1,500. It's basically the same thing you had like 5-10 years ago. They just like the what's on the label doesn't mean anything. Okay. So
Even buying through Amazon, you'll run into that.
yeah.
Where it's like the #1 rated battery on Amazon, everyone buys them, and then you actually go through and test. They would say 3,000 and you get 2.
So this is the end of the slideshow apparently. I don't think I have any more slides. However, I have a bunch of crap here, so if you guys want to come around, I'm going to try to fake like I know what I'm doing with these and show you random stuff. So this is a piece of EL wire that I took a photo of, and I kind of wanted to show you what it means like when it's tiny. Please come ahead, come over here. I don't want to go around everybody. Yeah.